the last thing I wanted to talk about is the inverse function property, because I didn't have time to do this, and the activity for this week does ask you to solve this. And it's a little bit hard to read between the lines if you don't really get what the property is saying. So the inverse property says, let f be a one-to-one function, again, hence being invertible, with domain A and range B. The inverse function f to the minus 1 satisfies the following cancellation properties. It says f inverse of f of x equal x for every x in A, and all that's saying is that when it's valid in its domain, and f of inverse of x equals x for every x in B, again, in its valid range. It says conversely, any function f inverse which satisfies these equations is the inverse of f. And really all that's saying is that if these two conditions are true, then f is the inverse of f and f inverses are inverses of one another in either way. And I know I didn't say that very well, but basically f is the inverse of f inverse is the inverse of f. So going both ways. But this is an important thing about inverse. If f has an inverse f inverse, the original function is an inverse to the inverse. They always kind of switch back and forth. And it's kind of obvious when you think about it. But if f has an inverse, they're both inverses of each other. They're kind of they both work in the way they do. And notice that it phrases them as what we call the cancellation properties. And this is a really important idea going further, because the idea of a function inverse is that if I want to cancel it out, I can apply the inverse to do so. And it's very important for solving an equation. When we talk about solving other types of equations in the next few chapters, chapter 4 through 6, really, we're going to be using inverse functions a lot. And that's the reason why inverse functions are so important is because they cancel the original function. And so, like, going back to, I wanted to look back at an example previously. Like, we looked at an example of x plus 4 and x minus 4, and I wanted to say, well, why are these inverses? But before I get into that, I briefly talked about this in class, but we were running low on time. Why is the inverse property true? And what it said is basically if I have f inverse of f of x, that is equal to just x. And f of f inverse of x is also equal to x. And again, it was for the specific values of x within their domain and range. And first of all, I want to say, well, why is this called the cancellation property? But because notice that what I have left over is simply x, the input. And so one of the ways we often could think about this algebraically is f inverse will cancel out f and produce simply x, the domain. And there's a really obvious reason that this happens with inverse functions, which is I wanted to bring this up because how would you ever remember this property? It's very weird seeming if we don't read between the lines. But kind of the nature of an inverse function is that, well, you know, if I have a function and it's normal, I have the domain and the range input output. The idea of an inverse function is to take the answer, like again, let's say I plug in 2 to a function and what would come out would be 5. An inverse function, what should happen is if I take the element of the range, plug it in, what should happen is it should turn me back into the element of the domain. It will reverse the point, give me 5, 2, and it will undo everything that original function did, assuming it's the proper inverse. But the idea of the inverse function property is if I were to chain them together consecutively. Whoops, what is this? Oh, I must have clicked something on accident. But if I chain them together, stack them f inverse of f of x, aka compose them in order, well, this would mean send it through f first, because I would have x of f of x, then of f inverse. Well, you get what I mean, but we talked about this when I was talking about compositions in 2.6, composition of functions. But basically, that's exactly what I have. Like, say, for example, I started here, and I first sent 2 through the f of x, so I would have f of 2, and I would get 5 as my answer. Again, I'm just making up numbers to make a point here. If I were to then send the answer back through the function, what I would get back is exactly the input, right? If I did f of 2, I would have 5. But if I then did f inverse of 5, it's going to take me back to the input. And that's exactly what this statement is saying, is if I take f inverse of f, it will take me back to whatever I started with, x, the element of the domain. Or algebraically speaking, we should have a complete cancellation of everything except for what I will have left over is x. And the same is going to be true if I start with f inverse. If I plug into f inverse first, then I send it back through the original, it's going to return back to whatever I started with, x. And again, technically that you would say, well, shouldn't that be the element of the range? Why is it x? But when we're switching between functions and their inverses, we're switching what is the input. So the role of x is changing. So it would be like I'm starting with x here, and the output would be f inverse of x. But again, inverses are inverses of each other, so they're both invertible. So like which one's the domain and range? Well, it doesn't really matter anymore because it's kind of arbitrary. It depends on which one you're talking about because they have flipped domain and ranges, if you see what I'm saying. Okay, so let me actually show you what I mean, because what in the last question of the second page of the activity, I asked you to verify using the inverse property, and I wanted to teach you how to do that. What do I mean? But basically, what you have to do is you have to check these two conditions and make sure it works. And essentially, what I want to do is I want to plug the functions into each other. So like if I was going to check f and g here to see if they were inverses, I would want to see, well, what happens if I take f of g of x? And what happens if I do g of f of x? And what should happen is if g and f are inverses, is those should cancel out, and all I should be left with is x. That's it. And basically all of the algebraic behavior of those functions should properly cancel each other out. If they don't properly cancel, they are not inverses. So let's go ahead and do that. So f of g of x means to plug g into f. So g is x minus 4. In this case, you know, these are pretty simple inverses because one's just x plus 4, one's minus 4, and I kind of talked about why that made sense today. We can also check, this is just a different way to verify that they're inverses, and we can see the algebraic benefit of knowing a function and its inverse going forward. That's why this is so important. But if I plug x minus 4 into f, well, that means I'm going to replace x with x minus 4. That'd be x minus 4 plus 4, right? Because f of x is that whole thing. And I'm plugging specifically g in for the x value, right? Because that's the g function, which is going in to f of x. And so what I would be left with is x minus 4 plus 4. Of course, minus 4 and plus 4 make 0. But notice what I'm left with when I compose them together is just x. And that's because functions which are inverses will cancel like that. Always. That's the benefit of knowing inverses and why they're so important in math in general. And why if you know a function, if you know its inverse, you can solve its equation. It's a very important thing to know. But you have to check both, not just one, because that is first a verification that, okay, the inverse property holds for the first direction, but if I compose them in the opposite order, g of x, it should do the same exact thing. So basically, if I plug f into g, does it make x or not? So that would be g of x plus 4. I'd plug in x plus 4 into g, which would be x plus 4, then minus 4. Of course, those would cancel in the same way, which would leave me with just x. Again, it would verify. This one was really easy to do because it was a pretty simple function, but that same inverse property should hold for all of these other ones as well, that if you plug one into the other, they should cancel each other out properly and produce simply x. And so what I want you to do on that last page is to verify in that way. So summarizing this chapter, this is a lot longer than I thought it would be. You can find an inverse function by applying the steps. You know, changing f of x to y, interchanging the role of them, and solving. Which, as we've seen with a couple examples, sometimes easier said than done, but sometimes it's possible. Again, assuming it's invertible, we should be able to do it. Hypothetically, again, if we know how. And you know, when we learn new functions, or you know, just review things like sine, cosine, log, e to the x, so forth, we'll always be thinking about similar, well, what's its inverse? How do I solve equations? Because it's kind of the same idea. But basically, that being said, that's how we find an inverse. And then there's various ways to sort of use inverses or check to make sure the inverses are correct. Like we could see, is the domain and range swapped? Is it a proper graphical reflection? Which is, again, just a result of the same thing. It should change the order of everything and create the opposite operation in the opposite order. And lastly, we could check via inverse property. This is like the algebraic way to verify. And if you really, this would be a way of proving it's an inverse, because if I show these two things are true, then by the inverse function property, that it has to be its inverse. And basically those functions are both inverses of each other. So f and g, we could say that this is f and this is f inverse, or this is g and these are g inverse, whatever, either way, cool. That will wrap up chapter 2. And in the next little lecture module for Friday, we'll start on chapter 3. I did not intend for us to have so much extra stuff because I did want to give you guys all Monday off, because it's, it is a holiday. So I want you guys to have a little bit of time to catch up. But anyways, I didn't want to leave you guys hanging with a lot of these ideas that we ran out of time for today. Cool.